All right, this practice problem reads, two piloted satellites approaching one another at a relative speed of 0.25 meters per second intend to dock. The first has a mass of 4 times 10 to the third kilograms, and the second has a mass of 7.5 times 10 to the third kilograms. We want to calculate the final velocity after docking of these two satellites. Then we're going to look at the change in kinetic energy of the system, and then we're going to look at that first with that first satellite being at rest. So the frame of reference of the first satellite, then we're going to repeat that with the frame of reference of the second satellite. See how that affects our situation. Okay, so these two objects are having a collision, and it's an inelastic collision, so they're going to stick together. And so in any collision, inelastic or elastic, we remember that our initial momentum is the same as our final momentum. So a collision situation, our initial momentum and our final momentum are the same. Law of conservation of momentum. So we want to make sure we understand what the initial condition is and what the final condition is. So our initial condition is these two satellites, and they're going to dock, and we're told that they have a relative speed of 0.25 meters per second. And if this is satellite 1 and this is satellite 2, we want to look at the frame of reference where the initial velocity of satellite 1 is equal to 0 meters per second. Now they're coming at each other, which tells us then that the initial velocity of satellite 2 is towards satellite 1. So as I've drawn it, that means this is 0.025 meters per second in the negative direction as I've drawn it if we use convention for our directions. So the relative speed, meaning they could both be moving, but relative to one another, they're moving at 0.25 meters per second. If that is in the frame of reference of that first satellite, that satellite will be at 0, and I've drawn it so that that other satellite is coming at negative 0.25 meters per second. Okay, the question is, what is the final velocity once these two dock together? So our final situation has these two satellites docking together. All right, and moving off. Now, if we imagine what's happened, if this one's coming towards that one at rest, they're going to move off. So we predict that final velocity is also going to be negative. Okay, so let's look at that first part. We have initial, of course, of the system equals final of the system. So that means our initial of 1 plus our initial momentum of 2 has to equal the sum of the final momentum of 1 and the final momentum of 2. 1 we said was not moving, therefore it has no initial momentum, so that term is going to be 0. And we also know that they dock together, so our final velocity of 1 is going to equal our final velocity of 2, and we're just going to call that V final. So, object 2, we have mass 2, initial velocity of 2 is our momentum of object 2 initially. Then we have mass 1, V final 1, which we know just to be V final, plus mass 2, V final also, since it's V final 2. So I have mass 2, V initial 2, just to show you that we can actually, in an inelastic collision, combine these two together and solve for that final velocity. All right, so we have all the information we need. Mass 2 is 7.5 times 10 to the third kilograms, and it's traveling at negative 0.25 meters per second. Then we can add these two together. So we have 4 times 10 to the third kilograms plus 7.5 times 10 to the third kilograms, and solve for that V final. And when we do that, we find that this is minus 1875 is equal to, if I add these two together, get 11,500, and we find that V final is equal to negative 0.163 meters per second. All right, so that's my final velocity, part A of this inelastic collision. Part B says, well, what is the change in kinetic energy of the system? Well, if we wanted to look at the change in kinetic energy, we want to look at our initial kinetic energy And we want to look at our final kinetic energy. And we'll do our change in kinetic energy, final minus initial. So what is our initial kinetic energy? Well, our initial kinetic energy only has one object moving. And object 1 is not moving. It's just object 2. So kinetic energy initial is equal to 1/2 mass 2 times the initial velocity of object 2 squared. So that's 1/2, 7.5 times 10 to the third. And our initial velocity is negative 0.25. When I square that, that negative, of course, disappears. And we know energy is a scalar quantity, so it's always going to be positive. That kinetic energy is 234.38 joules. What about our final kinetic energy? Well, I have this whole system now moving together, so its mass is the total mass. So 1/2 m total times our final velocity squared. That's 1/2, 11.5 times 10 to the third, times our final velocity of negative 0.163 quantity squared. And our kinetic energy final then in this case is 152.78 joules. So I lose my change in kinetic energy of the system is 81.59 joules. I lose 81.59 joules of kinetic energy in that system. That goes to some other type of energy, right? So we don't ever lose energy in the global system. Energy is conserved, but the kinetic energy of this system is not conserved. So I'm just going to pop that, well, we'll keep that number right there, I guess. Part B says, well, what if I change my frame of reference and I look at object 2 as stationary? So in this case, object 1, I'll do that in a different color, is moving at 0.25 meters per second in this direction. And object 2 is equal to 0 meters per second. Now, when they collide, we in this case expect our object to be moving to the right. Now, you might think, well, how can the exact same thing have one object moving to the left when it collides and one object moving to the right when it collides? Well, it's all about what our frame of reference is. And so if I'm riding on object 1, I see object 2 coming towards me and we move off together. But we could both be moving to begin with. If I'm riding on object 2, I see object 1 coming towards me and we move together. So relative to what I'm looking at, we've got to remember that that's a relative velocity, not an absolute velocity. Okay, so same process exists in this situation where our oh, this is very squeaky erasing today. Our momentum still has to be conserved. And now we're just going to practice that same idea. But I'm just going to erase this half of the equation because the second half actually doesn't change. We'll see that in just a minute. But the answer will. Okay. So I'll do this one in pink. So M1 V1 initial plus M2 V2 initial has to equal the system's momentum on the final. So M2 V1, oh, for heaven's sakes, getting ahead of myself. M1, mass 1, V final, again, they're the same, plus M2 V final. All right, well, in this case, M1 is 0. So we're left with, on the left side of the equation, the initial velocity. That was last case. Let me erase that. M1, V1 initial. M2 is 0 in this case. So on the left side of the equation, we have M1, V1 initial. And when we do that, we have 4.0 times 10 to the third kilograms times 0.25 meters per second. And that gives us a final velocity of 0.0869. All right, meters per second. So that's a final velocity of 0.0869 meters per second of these two objects when the frame of reference is on object 2 is stationary. So what does that change about my kinetic energy change? Well, in this case, only object 1 has any kind of energy. And so instead of the initial kinetic energy of the system being 234 joules, we now have an initial kinetic energy of the system being 125 joules, because mass 1 is a smaller mass, so it's going to have less kinetic energy. In similarity, the final kinetic energy of the system is not going to be 152 joules, because we're now moving at a lower speed. But instead, the final kinetic energy, since the speed is less, is 43.42 joules. So that relative speed is smaller, and so that final kinetic energy is smaller. But if I take the difference between these two, I get the same change in kinetic energy. Why is that? Well, that's the energy of the whole system. And so the change in kinetic energy of this system had to go somewhere outside the system, the global system. We can't totally lose energy. We lose energy within these two objects, kinetic energy. But the energy of the system, sound including the heat generated by that collision, all that total energy, what's lost in kinetic energy has to be converted to something else. And that remains the same. All right, so just two ways to practice two opportunities to practice our inelastic collision equation and idea, and just really it's conservation of momentum. So we just follow that same process, whether it's inelastic or elastic. In this case, kinetic energy is not conserved like in an elastic collision, and so we can just practice that twice, looking at those two different frames of references, but kind of gives us an idea of how the change in kinetic energy has to stay the same. All right, good job.